Sounds are governed by principles of physics, from the vibration of strings on a violin to the measurements and dimensions that go into the acoustics of a concert hall or stadium. At the heart of the physics of music is the wave, an energy-carrying disturbance that travels through particles in a given medium. When struck, a tuning fork vibrates at a single particular frequency. The constant movement of the prongs back and forth causes repeated sound impulses, which are really disturbances in the air. The prongs hit the air, and the air continues to hit neighboring air molecules. At one instant, some molecules are close, while others are further apart, a phenomenon known as condensation and refraction of air. Vibrations in air are called traveling longitudinal waves, which we can hear. Sound waves consist of areas of high and low pressure called compressions and refractions, respectively. The height of the wave, or the amplitude, is what affects the volume of the frequency. And darker areas are high pressure, compressions. One wavelength of the wave is highlighted in red. This pattern repeats indefinitely. Marin Mersenne, a 16th century French mathematician, devised three laws to calculate the frequency of the fundamental tone produced by a string. Together, they state that the frequency is inversely proportional to the length, proportional to the square root of the tension, and inversely proportional to the square root of the mass per unit length. The lowest resonant frequency of a vibrating object is called its fundamental frequency. Most vibrating objects have more than one resonant frequency, and those used in musical instruments typically vibrate at harmonics of the fundamental. Overtones are the other frequencies besides the fundamental that exist in musical instruments. Instruments of different shapes and actions produce different overtones. The overtones combine to form the characteristic sound of the instrument. Because their overtones are different, their sounds are different.